Hey everybody, Dr. A here, and in this video we are tackling a third example of systems of equations using the graphical method. So in our given information we are told to use the graphical method to solve this system here, x plus y equals 3 and x plus y equals 1. So if you recall, the graphical method is best used for two equations with two variables, and it really becomes inefficient when you have larger systems than that. And the way we apply this is we simply graph those two equations on the same set of Cartesian axes. So let's go ahead and tackle the solution. And as I've mentioned in several of my other videos, you want to write this down. Don't just watch and listen. Write this down, take notes. That's how you learn the best. So if you've watched the previous example videos on the graphical method, what we typically find most convenient is to rewrite the equations in slope-intercept form. So if we rewrite them, our first equation becomes y equals negative x plus 3, and our second equation becomes y equals negative x plus 1. Now we are ready to conveniently graph this system of equations. Now, one thing you may have noticed, and we're going to see how this kind of unfolds when we graph this system, is that both equations have the same slope. The slope of both of our equations is -1. So let's see how this plays out when we graph it. So I'm going to draw my set of Cartesian axes. Remember, our x-axis is horizontal, our y-axis is vertical. I'm going to scale off my tick marks here to measure some values here, 1, 2, 3, 4, 5. Now, on your paper, if I were you, I would use a straight edge or, a credit card or a student ID or a ruler or something, so you can draw a really nice straight line and straight lines when you are making these plots. Make your plots look good. I'm just doing it quickly on this video, so mine aren't looking as nice as you can make yours look. All right, so let's go ahead and plot this first equation. Our y-intercept is the point 0, 3. So here is our y-intercept of the first equation, and we have a slope of -1, seen by the coefficient of the -1 times x here. That means that our linear equation is decreasing here, so we can plot some points like this. We have a rise over run heading in a negative direction. So here's our first equation, okay? Y equals negative x plus 3. Our second equation has a y-intercept of 0, +1, so that's going to be right here. And again, it has the same slope, -1. So that means we have a rise over run of -1. And we can generate this line just like this. Now, although my lines aren't perfect, because, as I mentioned, I'm not drawing this very perfectly on this video, but you should on your own paper, these are parallel lines. So our second line, I'm going to write it down here, y equals negative x plus 1. We can say, since these lines have the same slope of m equals -1, they are parallel, okay? Now, parallel lines never intersect. They never meet. Thus, this system has no solution and is inconsistent. Okay? So anytime you have a system of two linear equations that have the same slope, okay, no matter what that slope is, if it's the same slope, that means that a graph of those equations would give you two lines that are parallel to one another. Now, parallel lines never intersect, okay? And if you draw your parallel lines to scale with a ruler or a straight edge and make them look nice and neat, a lot better than what I've shown here in this video, then you will see that they will never intersect. They'll never touch each other. And that would mean that that system has no solution, because a system has a solution based on where those lines intersect. And if they never intersect, that means there's no solution. And another way of saying that a system has no solution is calling it inconsistent. So hopefully this kind of helps you understand the idea of parallel lines and why a system of equations of parallel lines has no solution. So please hit like and subscribe on the video, and we'll see you next time.